Hello, today we are taking a look at Calculus 1 derivative notation and rules of differentiation. So we're going to start off by taking a look at some vocabulary. A derivative is the instantaneous rate of change or the slope of a function at a point. This can be proven with the limit definition of a derivative, and we will take a closer look at that later on. To derive is the process of formulating an equation based on previous laws, equations, or rules. To derive should be not confused with to differentiate, which is the process of finding a derivative. Throughout the rest of your calculus course, you're mostly going to be differentiating instead of deriving. So just to get those clear, deriving is actually formulating a new equation based off of things that you are given, whereas differentiating is taking the derivative. Now let's take a look at some notation that you'll see. The most common forms of derivative notation you'll see is the Lagrange and Leibniz notation. The Lagrange notation is written like this. So f with an apostrophe of x. And these are taking the derivative of a function f of x. But they could also be taking the derivative of y. So Lagrange, we are taking the derivative of the f of x function, and we are notating that with this apostrophe, which we call prime. So f prime of x means the derivative. This could be also written as f double prime of x for a second derivative, or you could continue and you could write f of the third derivative or any number as so. You might also see this as f with Roman numerals, so this would be the 10th derivative of x. For the Leibniz notation, which is another very popular one, is written as dy over dx. So this is differentiating your function of y with respect to x. You may see this as d squared dy over dx squared for the second derivative. And the same thing could be written for the 10th derivative, d10 of y over dx to the 10th derivative. Newtonian derivatives are written similarly to Lagrange. However, they write it as f of x with a dot on top, which may also be written as f 2 dots for the second derivative. And then our last one here is Euler notation, which you may see as d of f of x. But these bottom two, the Newton and Euler notations, are less common. The ones that you are most likely going to be running into in your Calculus 1 course is the Lagrange and Leibniz notation. So let's get started and take a look at the rules of differentiation. These rules are going to be applicable to the rest of the rules that we go over for the rest of this calculus course. So these are important rules to lock down and remember. We will go through a little bit of a reasoning of why these rules make sense, and we'll do some practice problems later on. To start, the constant rule is going to be written as so. D over dx of c, a constant, is equal to 0, where c is any real number. The rule for coefficients is if you have a coefficient in front of a function, c f of x, this is equal to taking that coefficient out front and multiplying it by the derivative of the function itself. Again, when c is a real number. The addition and subtraction rule is as so: d dx of f of x plus or minus g of x is equal to f prime of x plus or minus g prime of x. So what this rule is saying is that if you have two functions that are being added or subtracting to each other, then you can actually go ahead and take the derivative of each individual term and then add those together to get the full addition and subtraction derivative. However, this should not be confused with multiplication and division. So this, what I'm writing in red, is not true. And we will go over this in a little bit more detail in a bit. And then in a future lesson, we will go over how to do multiplication and division properly. So if you have the derivative of f of x times g of x, this is not equal to f prime of x times g prime of x. So you can't go and multiply them together, and we'll see more later. And our final rule of today is power rule, which is d dx of x to the n is equal to n x to the n minus 1, where n is a real number. So this is saying if you have a function where x is raised to any number and it's just x, right? Just x here is raised to any number, then the derivative is that number times x raised to the power of that number minus 1. So why are these rules the way they are? Well, to start, we have the constant rule here, right? And remember that the derivative is the rate of change of something. It's the slope on a graph. So if we look here at our constant rule, right, if we have that y equals 6, that's a constant value. So our slope here is a straight line. And we can go ahead and plug this into our slope formula and find that the point at 4, x equals 4, is 6, and the point at 1 is also 6. So that's going to be 6 minus 6 over 4 minus 1, and we get our slope as 0. And recalling what a derivative is, it's the slope of a line. So it makes sense that if we have a constant, the slope is going to be 0, and therefore the derivative is 0. For our coefficient rule, remember that is saying that you can take that coefficient out front and then multiply it by the derivative later on. So let me just rewrite these again. So the constant rule, right, is if you have d dx of c, this is equal to 0, which we proved here that the slope is going to equal 0. The coefficient rule is d dx of c times f of x is equal to c times the derivative of f of x. And here we have two different functions, right? We have y is equal to 2x and y is equal to x. So if we look at the derivative of y equals x, the red line, our slope is 1. And so our second line in blue, y equals 2x, well, y equals 2x is just 2 times the red y, right? Because the red y is equal to x. And we know that the derivative of y is going to be 1. And so the derivative of y, the blue y, is going to be 2 times the derivative of the red y, which is just 1, and so the derivative of the red y, or the blue y, is 2. And then finally here we have our addition and subtraction rule. So the way that I like to think about addition and subtraction with rate of change is if you imagine that you have a stick. So here we've got a stick of two parts. We've got a blue part of our stick and a red part of our stick. And at the beginning, the blue part of the stick is 2 inches long and the red part of the stick is 2 inches long. and the blue part is increasing at a rate of 2 inches per second. So that's the derivative, because it's a rate of change. That's how fast it's changing. It's a slope. And the rate of the blue, or the rate of the red, is increasing at 3 inches per second. So if we look at our first time slot here at 1 second, right, we've got 2 inches of blue and 2 inches of red. And so our total length is 4 inches. And then 1 second later, at 2 seconds, our blue line has increased by 2. So now it's at 4 inches. And our red line is now 5 inches because it's increased by 3 inches per second. So our total length of the line now is 9 inches. If we look again at 3 seconds now, our blue segment is at 6 inches and our red segment is at 8 inches. So our total length is 14 inches. Now we can go ahead and take a look at the rate of the stick by doing some slope formulas between the total length and our time. So we took 14 inches minus 4 inches divided by 3 seconds minus 1 second. And we get 10 inches per 2 seconds, or 5 inches per second. And that's our rate. So our derivative, d dx, of this line is equal to the rate of the blue, I'll write as blue prime, plus the rate of the red, so r prime, right? Because prime is the derivative, so the total rate of the line is the rate of the blue part plus the rate of the red part, which is equal to 5 inches per second, which is exactly what we have up here. 2 plus 3 is 5, and that is exactly what we got. If we take a similar approach with multiplication, though, it's not going to work the same. Because if you think, right, multiplication, when we first learned about multiplication, we did it with area. So we can look at area again, right? And if we have the rate of our blue line at 2 inches per second, and the rate of our red line growing at 3 inches per second, if we look at our first time slot, if we have 2 inches to start on both sides, then our area is going to be 4 inches. And then 1 second later, our red line has grown by 3 inches, so now we're at 5 inches, and our blue line has grown by 2 inches, and so now it's 4 inches long. So our total area is at 20 inches. Once again, at 3 seconds, now our red line is 8 and our blue line is 6. And so our total area is 48 inches. And if we look at the rates of each one using our slope formula, we've got 20 inches, these should really be squared, right, because it's area, minus 4 over 2 seconds minus 1 second, we get 16 inches squared per second. I'll put a square on all of these, right? From 2 to 3, a similar thing, right? We get 28 inches squared per second. And then from 1 to 3, we would get 22 inches squared per second. And that's different for each one, right? But if we actually go ahead and we look at what we have here, and we do the rate of the blue, that is the wrong color, the rate of the blue times the rate of the red, we would get 2 times 3, which is equal to 6 inches per second, which is clearly not true. We didn't get that in any of our options here, and each of our options are different, so something else is going on here, and because of that, we're going to have to look at another rule for multiplication and division, which we will look at next time. So the important thing to remember for today is that if you run into a problem with multiplication, you're going to have to actually go ahead and multiply the entire equation out, and you can't just go ahead and assume that you can multiply the rates together to get the correct derivative. And finally, let's take a look at our power rule proof. So remember, the power rule is saying that if you have d dx of x to the n, this is equal to n times x to the n minus 1. Right? So this is saying, just as a quick example, is if you have d dx of x squared, this is going to equal 2 times x to the 2 minus 1, which is equal to 2 times x. And a quick proof here is if we're assuming that n is any natural number, where f of x is equal to x of n, then let's take a look at n equals 0. Then we get x to the 0, which is just 1. And if we use our limit definition of derivative, we'll get our limit is equal to 0, which is also the same as 0 times x raised to the power of 0 minus 1. So that is 0. With 1, we can do the same thing. That's x to the first power. We get x plus h minus x. The x's cancel out, and we get h over h, which is 1, which can also be written as 1 times x to the 1 minus 1, which is just 0, and any power raised to the 0 is 1. And then with 2, that's x squared. We plug that in, we get x plus h squared minus 2 all over h. We FOIL this out, and we get our polynomial here. Our x squareds will cancel out, and we're left with 2x plus h, or 2xh plus h squared over h. And we can take an h out of both terms, and we get 2x plus h. And then we do the limit as h approaches 0, we just get 2x. So this is written as, right, 2x to 2 minus 1, which is 2x to the first power. And you can go ahead and prove this with any number that you'd like using the limit definition of derivative. So let's take a look at some practice problems. This is exactly what we just did, so remember our power rule. Power rule of d dx of x to the n is equal to n times x to the n minus 1. So here, our n is equal to 2. So our derivative is going to be 2 times x raised to the 2 minus 1. So 2 minus 1 is going to equal 1. So this is 2 times x to the first power, which is 2 to the x. For our next problem here, right, we're going to remember our power rule, and then we're also going to include our two other rules, which is d dx of a constant is 0. And then for addition and subtraction, we have d dx of f of x plus or minus g of x is equal to f prime plus or minus g prime. So if we go ahead and do this, we can do this in 3 different parts. So if we break this apart, we can write d dx of 4x squared minus d dx of 10x plus d dx of 4. So here we are finding the derivative of each individual term. So our first one, we're finding the derivative of 4x squared. So we're going to do that the same way with our power rule. And this part is going to be 4 times our n, which is 2. 4 times 2 times x to the 2 minus 1. Now let's look at our second term here. We've got the derivative of 10x. So we're going to do 10 times, and remember that this x has a 1 on it, so we can multiply 10 times 1. And then we get x to the 1 minus 1. And then finally here, we've got just a constant. There's no x there. And so this is going to be our constant rule. This is going to be 0. And so we can write this out a little bit more. We get 8 times x to the first power minus 10. And that is going to be times x to the 0 power, which is just 1. So this is our final answer. Another problem here is we've got the derivative of this quotient of 6x cubed minus 2x over x. Now this one is a bit different and a little bit more intimidating than the other questions that we've looked at. But the way that you can simplify this is notice that you've got an x in every term of this quotient here. So we can actually write this as 6x squared minus 2. We just simplified a little. We took one x out of each thing and simplified it down. So now we can go ahead and use our constant and power rule to differentiate. And we get 6 times 2 times x to the 2 minus 1. And then our 2 is just going to be 0. So this is minus 0. So we end up getting 12x. And that's our final answer for this. And for our final problem here, we've got something interesting, which is d heart of d of 9 heart to the third plus 2 heart to the 3/4 minus 6 heart. So the point of this problem is to get you more comfortable with differentiating in terms of anything, because as we go on through the rest of the calculus course, we're going to be differentiating in terms of different things, not just x or y, but also time. And if you go on to calculus 2 or 3, you might see z or any other number of variables. So you have to be able to be comfortable with taking derivatives of other variables. And it doesn't even have to be a variable. It can be a symbol like our hearts here. But it's going to be the exact same thing that we've done, right? So we're going to break this apart by each term. And this is going to be 9. This is just a power rule, right? 9 times 3. And then our heart raised to the power of 2. 3 minus 1 is 2. And now we do our second term. And this one, again, is different than anything that we've seen so far because there's a fraction in the top. But remember, the power rule is with n is any real number. So you just do the same thing that we've done. And this is 2 times your n, which is 3/4, heart, and then you do 3/4 minus 1. And now for our last term here, right, we've got 6. And this heart is raised to the first power, so this is 6 times 1 times our heart raised to the power of 1 minus 1. And so we can go ahead and simplify. We get 27 heart to the second power plus 3/2 heart. This is 3/4 minus 1, so that's 3/4 minus 4/4, also known as negative 1/4. You can totally have negative powers, that's totally fine. And then lastly, we've got 6. Heart raised to the 0th power, which is 1. So this is our final answer right here.